This show me covers the simple machine screws. A screw is an inclined plane wrapped around a cylinder. It's also a wheel and axle used to create a rotational motion. A few of the important properties of screws is that it takes and changes a rotary motion or a rotational motion into a linear motion, meaning it pushes it into something. And it has a very large mechanical advantage. It also has a large amount of friction loss. If you ever screw a screw in or unscrew a screw, you'll notice that quite often the screws are very worn. Another item to keep in mind about screws is the pitch is the distance between the threads. Now, while I normally don't like the PowerPoint presentations that go with a lot of this stuff for Project Lead the Way, in this case I don't really have much of a choice because I cannot draw nearly as nicely as they do. So when looking at a screw, there's some important things to keep in mind. The effort arm distance, so that's going to be my DE. If you're putting it in there by your hand, then it's going to be the radius, this distance here, which is the radius of the actual screw. If you're using a wrench, it's the length of the wrench. The pitch, as you can see, is the distance between the threads, and it's the exact same distance that would happen if you do one full rotation. And the diameter of the screw is the actual diameter down here at the bottom. Now, the way that they actually label screws and the way you purchase them from places like Home Depot, they have this information here. The first set of numbers is the diameter. In this case, it's 1/2 or 1/2 inch. The 13 is the number of threads per inch. Pitch is actually determined by saying how many inches with how many threads. The way it is always viewed, though, is 1 over 1 inch over however many threads. In this case, it's going to be 13. So, following that, the pitch for this specific screw is 1/13 of an inch. What that means is that if I do one full rotation of the screw, it is going to go in to, whether it be the wood or the metal, a total distance of 1/13 of an inch. So for each rotation that I do on the screw, it goes in one pitch, or 1/13 of an inch. So let's go ahead and take a look at the ideal mechanical advantage of a screw. In this case, the identification information we need for this screw is here. This means that it's 1/4 inch in diameter down here at the bottom of the screw, and that it has a pitch of 20, which means that there are 20 of those little things per 1 inch. So if we look at IMA, it's still our standard distance of effort over our distance of resistance. Distance of effort is one rotation of the effort arm. For instance, if there is no wrench and you're just putting it in by your hand, it is one rotation, this distance across here, from the middle of the screw to the outside edge of it. Our distance of our rotation, our distance of our resistance is going to be the pitch. It's how far it's going to go into the substance whatever it is I'm screwing it into with each single turn of the effort arm. And since we had talked about this with wheel and axle, circumference is the area around a circle. So what they're looking at is this, they were looking at this area here, but they were looking at it as it went all the way around. And that's kind of that is one full. So the formula for circumference is 2 pi r, and we put that over our pitch. This is just a formula that we use for screws. So looking at the example, down here at the bottom, it's asking what the ideal mechanical advantage of the screw is if effort is applied by an 8-inch long wrench. So what we're doing is we're applying a wrench to this, and it's coming out 8 inches. So right off the bat, I know the the radius of this circle is going to be 8 inches, because that's the length of the wrench. So multiply it all out. I have 2 times pi times 8 inches, and I divide that by 1 over 20, and I end up getting the answer 1005 is my ideal mechanical advantage. So looking at a continuation of the previous example with our ideal mechanical advantage, applying it to our actual mechanical advantage, we're looking at our forces. So, still using the same screw, still using the same 8-inch long diameter, or 8-inch long wrench, I'm going to apply 35 pounds of force, which happens to be my force of effort, into the screw, and it's going in 1,200 pounds, or that's how much resistance we're overcoming to get the screw in. I put the 1,200 over my 35, divide it out, and I get a 34-to-1 ratio, or I put in, if we write it like this, I put in 1 pound of effort for every 34 pounds of resistance I'm overcoming. To find out how efficient this is, we use our efficiency formula that we've been using all along, which is my actual mechanical advantage of 34, divided by my ideal mechanical advantage of 1005. I multiply that by 100 and find that my efficiency is 3.4%. Here they're asking us why the efficiency is so low. I pose that question to all of you to give me an answer on your own. So the last topic to cover with our simple machines are compound machines, which are just a number of simple machines working together to complete a task. A bicycle is one good example. We have levers, we have wheels and axles, we have gears, a lot of things working together to help us out here. To calculate the mechanical advantage of any compound machine, it's just a fairly simple formula. I take the mechanical advantage of each of my individual units and multiply them together. That's using either my ideal mechanical advantage or my actual mechanical advantage, as long as I use the same for all of my different simple machines.